के रखें दोनों पे, कहीं पे भी डाउट आ रहा है ना. All right. Okay. Good morning, everyone. So after this havoc, we are able to start this session. Okay. So my name is Santosh Verma, your mentor for GATE course. Okay, and we'll start with the digital logic and design. So this is the very first course, and before going to start this session, I just want to introduce you about the gate, like what are the total weightage and how the marks distribution will be there, whether it is completely positive or completely negative, or some partial marking is possible or not. Okay, and then we'll brief about the basic introduction of the digital logic design, this particular course, what is the syllabus, and what are the important topics that has to be covered uh, before you appear for the exam. Okay, so we'll start with the syllabus. So that syllabus covers the number representation that you are very much familiar with this, that the computers, being computer science, that computer is only able to understand 0 and 1. Okay, and whatever we are using in daily life is decimal. Okay, and the addresses are referred as unsigned integer or hexadecimals most of the times. Okay, so we need to have the mechanism to represent these different types of number systems and the conversion between each one. Okay, so binary to decimal, decimal to binary, or octal, and so on. So we'll see that particular conversion over here, and then we'll see the computer arithmetic, like if we want to have certain addition, subtraction, multiplication on integers or in floating point. So how floating point numbers are going to be represented in memory. Okay, how signed number is going to be represented in memory. So all this has to be taken care in this computer arithmetic. Then we'll see about the Boolean algebra. Okay, so like in linear algebra, you have seen that the matrices are represented and they have certain properties. Like if you want to multiply two matrices, in that particular case, the dimension will play the important role. Okay, you cannot multiply two random dimension into uh, one. Okay, so in that particular case, there are certain relation between the dimension and so on. So similar to that, certain identities are there related to the binary variable. Okay, so we'll see that particular part in Boolean algebra, and that will play a very important role in simplification of algorithms. Like you have certain function, okay, you have certain combination of logic gates, and the cost of that particular logic gate is going to be very high if number of gates are increased. So you know that in new era, your computer system or your chip must be the miniature, the smallest one. Okay, and it is only possible when we have the minimum number of logic gates in that. Okay, तो जितना ज्यादा हमने यूज किया उसके अंदर. Okay, let me know all the online users whether they are able to understand Hindi or not. Please write in chat box. If all are comfortable in Hindi, so I'll switch to both the modes. तो इसे completely इंग्लिश बनाने के बजाय मैं थोड़ा इंग्लिश हिंदी मिक्स करूं. प्लीज कंफर्म ऑन जूम. सभी कंफर्टेबल हैं हिंदी में? ऑल राइट. सो नो. ऑल राइट. सो बिल्कुल नहीं आता या थोड़ा बहुत चलेगा? Okay, so considering this particular request, I'll complete this particular session in English only. All right, so what I'm saying that why Boolean algebra and minimization is required. Okay, so we know that day by day our chip system is going to be stringed in size. Okay, so on the same flatbed, on the same size of the flatbed, or you can say on a unit size of the flatbed, number of components are going to be increases day by day. That is nothing but the Moore's law. that every second year the number of components on a IC is going to be doubled. Okay, that exactly is not the correct, but that is almost matching. Okay, so every year the same IC is going to have the more capabilities. Okay, because you are going to increase the number of components on the same IC. Okay, so how to minimize if we are going to increase the number of gates, if we are going to increase the number of logic gates on that particular IC, so we need to have certain mechanisms so that we can simplify that particular function or simplify that particular combinational circuit, so that minimum number of logic gates are required to fulfill the our required outcome. Okay, so objective must be met, we cannot compromise with the objective, okay, outcome. So we need to have the mechanism to minimize that. So Boolean algebra and the minimization, that k map or the tabular method, okay, so that will play the important role here. Okay, so we'll see that two thing over here, and then we'll come to the combinational and sequential circuit. There are lots of circuits, okay, that is categorized under the combinational and the sequential circuit. So combinational circuit is that in which you have simply an input and the corresponding output is produced. So output is going to be directly dependent on the provided input. Okay, so that is your, like, you can have the AND gate. Okay, that you can also treat as a combinational circuit. Simply AND gate can be treated as a combinational circuit, that you are supplying two input or one input, and that is going to be produced according to the AND logic. Okay, so similarly, like, not only the AND, any logic gate or any combination of that logic gates can be simply representing the combinational circuit. So that is the combination of gates, that is why it is known as combinational circuit, and that is going to be the output is going to be directly dependent on the input value. Okay, and in sequential circuit, the output is dependent on input as well as the previous state. Okay, so some memory element is going to be stored so that it can check the previous state. Okay, so output is dependent on the state only, or state as well as input, both. Okay, so can you recall any automata which is resembling this property? Your output is dependent on current state only, or your output is dependent on current state as well as the input? So any automata that you know that has certain output. Yes, Mealy machine and Murray machine. So you have the finite automata. Okay, so see, the things are very much connected. You can't say that courses are entirely different, ye padhu, ye nahi padhu, then it will go on. Okay, the courses are very much connected. Okay, then कंप्यूटर ऑर्गेनाइजेशन जब पढ़ाऊंगा तो वहाँ पे भी आपको चेक करना होगा कि वो हार्डवेयर से रिलेटेड है, एंड दैट इज फर्दर रिलेटेड विद द ऑपरेटिंग सिस्टम एज वेल. ओके, एंड जब ऑपरेटिंग सिस्टम पढ़ा रहा हूँ तो आप वहाँ पे भी आप चेक करोगे कि वट एवर इज द हार्डवेयर रिलेटेड टू देयर इज वेरी मच कनेक्टेड विद द COA. Okay, and COA is very much connected with this particular course, digital logic. So there must be a proper sequencing whenever you study for the gate exam. Okay, it is not like that कि आज मेरा operating system पढ़ने का मन है तो. Okay, before that you have to complete the prerequisite. All right, so whatever sequence we follow is very coherent to that particular requirement. Okay, so this is the corresponding syllabus that is going to be covered in this particular case, and the gate exam covers the 4 to 5% weightage for this particular course. Okay, so since weightage is low, you cannot ignore this, because this 4 to 5% is 100% achievable. Okay, so if you go through this particular syllabus, if you go through the PYQ, go through with the practice, you can gain 100% out of this. Okay, and 4-5 marks are very important. Okay, so just look at the particulars that what the things we are going to cover over here. Let me sync my pen first. All right. Okay. So here you can see that the duration of GATE exam is simply given as 180 minute, that you will have the 3-hour timeline to complete this particular paper. Okay. And if you look at the number of questions, that is only 65. Okay. So if you correlate with the time and the number of questions, you can see that we have the haptic number of time to complete this paper. Okay. But since questions are not so easy, they are not straightforward कि आपको सिर्फ 1 minute each question लगेगा and you can able to save the time. No, that will be very much logical, very numerical type. Okay, and in that particular case, this is going to consume the lots of time. So you have to have the more practice on the question and save the time. Okay, so it will require more than 3 hours. Okay, so this 3 hour is lesser for completing the entire paper. Okay, yeah. Okay, let me redo this. Is it visible now? Clear? So the students who are online, please confirm whether screen is visible to you or not. Okay. So okay. So we are talking about that the duration is 180 minutes and the total number of questions are 65, and out of this 10 questions are related to the aptitude. Okay. So this is straightforward that weightage to the core courses vary. Okay, like it is defined as 4 to 5% only, but sometimes it happens that it is 7 to 8%. Okay, so that varies. Like in the previous 2024 DA exam, DSA was supposed to be of 10% weightage only, but that comes around 15 to 16% weightage. Okay, so that depends upon the problem setter. But for this general aptitude, it is fixed thoroughly. Okay, so this is the first paper, and that is going to be of 10 questions. Okay, and the marks weightage is given as 15. Okay, so that has the 15% weightage of the entire paper because it is having the 100 marks. Okay, so and the 55 marks or 55 questions are related with the core CSE. Okay, in which all the core courses will be covered. Your engineering math, your discrete math, digital electronics, your computer organization architecture, DBMS, operating system, computer network, and all that, automata and compiler design. So all that courses comes under 55 questions. Okay, and the questions are of three type: MCQ, where only one question, the question has only one correct option. Okay, and the multiple selection type. In that particular case, the question may have one or more than one correct option. All right, and there is no partial marking, like there are three correct options and you have selected only two, so you'll get 2 by 3 of that particular weightage. No. Okay, if you have selected all correct three, then only you will be get awarded as marks, otherwise it will be counted as penalty. Okay, NAT, the numerical answer type. So most of the time the questions are bifurcated in 1 marks and 2 marks. Okay, so here you can see that question carry the weightage as 1 marks and 2 marks. and all the NAT and MSQ types are mostly classified at 2. Okay, if they are uh, having some depth in logic, then in that particular case, the marks will be increased in weightage. Okay. All right. If you look at this, okay, this last option is visible to you. Let me hide this. What happens? Okay. So here you can see that the negative marking, that for 1 marks it is going to be 1/3. Okay. For 2 marks it is going to be 2/3. Okay. So 30% is given to a negative penalty whenever you have the wrong selection. Okay. So you must go for the answering marking the answer of any particular question whenever you are 100% sure. Okay, if you are dicey in that particular case, you can leave the question. Okay, because you are not going to say putting a wrong answer only. You are going to see one question attempted, one question is wrong, as well as whatever you have done correct is also going to be reduced. Okay, so that wrong question or your wrong answer is not only penalizing for that particular question, that is also penalizing you in your correct answers. Okay, so attempt as much as possible, but maximum correct. Okay, if you are dicey in any particular question, it is better to leave that question. All right, and there is no negative marking for wrong answer in MSQ or numerical analysis, numerical answering type questions. Okay, so there is no such thing. Now let me jump to the current course, that this particular session will continue for the digital logic and design. Okay, so we'll see here the digital logic system and the computer system, how computer works, and then information representation like the number systems. Okay, binary, octal, decimal, hexadecimal, and so on. Sometimes it is also that straightforward known radix questions are not there. Okay, so in that particular case, you have some random base. You need to convert into the known one, and then you can further convert into the unknown type. Okay, so we must have the procedure known to us, familiar to us, that how we can convert one particular base to another one. Okay, then we'll see the arithmetic operation, base conversion, decimal codes, like there are lots of codes that is related to the decimal one. BCD is one of them. Okay, uh, then parity, gray code, and the alphanumeric code like ASCII and so on. Okay, so we'll see this particular topic in our first 2 sessions. Okay, so I'll start with the digital system, that you can have a digital information processing system. So this is the central part which is having certain, let's say, the state machine. Okay, you can simply consider it as a state machine that requires certain discrete input and produces the discrete output. All right, can you have any example of this? A digital system that requires an input and produces the output, and that requires discrete input. Calculator, you can say. Okay, that has certain digital input. Okay, that produces the discrete output. All right, sometimes you can store that particular value, or whatever you have calculated, you can store that particular value, so system state is also there. Okay, so whatever outcome is there, you have maintained into the particular system in the memory. Okay, and for a particular discrete time, you can further fetch it. Okay, so temperature reading system, humidity reading system, and all that similar kind of things, you can go for that. Okay, so in this particular case, you can have the 2 things, whether there is no state present or there is state present. Okay, if there is no state present, then straightforward you can say it is a combinational logic system. Okay, If there is no state present, that means you are not able to see the previous outcome or whatever outcome related to that particular value in the previous timestamp. Okay, if you are not able to manage that, in that particular case, you can see it is nothing but simply combinational circuit. Okay, combinational logic. So your function of output, you can say your output is directly dependent on a function of input. Okay, so in this particular case, no other state is required. So output is directly proportional to the input, directly dependent on the input. Now see, if there is state present, in that particular case I told you that whenever there is any state presented, that state must be updated with respect to the discrete timestamp. Like whatever is the value stored with respect to the previous timestamp. Okay, so past value क्या थी वो check करना है आपको. In that particular case you must have the state. Okay, and that state, maintenance of that particular state is nothing but the memory. Okay, that is going to store the certain value. Okay, so if it is updated with respect to the discrete time, then it is called as synchronous sequential system. Okay, so it is state present is simply representing the sequential circuit. Okay, and now it could be synchronous or asynchronous. If it is storing the value of it or it is preserving the value according to the timestamp, then it is synchronous, otherwise it is asynchronous. All right, now in this particular case you can see that your state is dependent on the function of state as well as input. Okay, your next state, whatever will be the next state, that is dependent on the current state as well as the current input. Okay, or you can say output is dependent on the state only, or output is dependent on state as well as input. Okay, so for this particular thing you can say it is nothing but the finite automata. Whatever is the next state is going to be the current state as well as the input. Okay, we simply represent it like q naught having an input a transiting to q1. Okay, so this is the first one, that is any finite automata, whether it is deterministic, non-deterministic. Okay, that is entirely different thing. This representation that whatever is the next state is going to be dependent on the previous state as well as the input. Okay, now look at this output. So this is simple finite automata, and if I associate output along with this, okay, so input over output, if output is dependent on state only, okay, and if output is dependent on state as well as input both, okay, accordingly you classify this finite automata as Murray machine, and this is nothing but the Milli machine. Okay, so I'm not jumping to that particular direction. Finite automata or the TOC subject will be taught by a different teacher. Okay, I guess immediately after this particular class. Okay, so I'm not jumping to that particular topic in detail. Just look at this. This is nothing but a digital counter that is going to count the speed. Okay, so this is the odometer that is going to count the speed of a vehicle. Okay, and this has a counter pin and this has the reset pin. Okay, so whenever you press a reset button, that entire value is going to be initialized with 0. Okay, so you can start your race again. Okay, and count up is simply representing the incremented value. So from 0 to till this particular distance you have traversed. Okay, and how this value is incremented, how odometer works. So every kilometer, whenever your wheel completes one rotation, okay, the wheel of your bike, wheel of your car, whenever that completes one particular rotation, it simply increments the value. Okay, so you can say that the wheel dimension is going to be fixed, it is not varying, na? Okay, and whatever is the accelerator, whatever is the velocity of your particular car, depending upon that, the traversal of that particular distance is going to be faster or slower. Okay, if your uh, vehicle speed is slow, in that particular case it is going to be more time taking to complete one particular counter. Okay, or if it is faster, then in that particular case it is going to be completed in lesser time. Okay, so this particular system is indirectly dependent on the time. Okay, so in that particular case, can we say it is synchronous or asynchronous? Your odometer is synchronous or asynchronous? Asynchronous. I just told you that it is dependent on time. Your odometer will only work when you start your vehicle, whenever you start traveling. So that will consume the time. And according to the digital timestamp, it is going to be incremented. So it is synchronous in nature. Okay. Doesn't matter whether you are able to understand this particular topic or not. Okay. I'll come to the further example with synchronous one. Okay. Now come to the digital system. Which hierarchy, which architecture is represented by this particular system is? Is it von Neumann machine or Harvard machine? Have you heard about these two names? Von Neumann architecture and Harvard architecture. Deepak, please have a look on Zoom as well if they have any doubt. Yeah. So which architecture is this? Von Neumann or Harvard? No idea. Can you differentiate between the microprocessor and microcontroller? Okay. So just have a look over here that memory is completely outside the CPU. Okay. Memory is completely outside the CPU. That means the central processing unit is simply having the microprocessor. Okay. Microcontrollers are having inbuilt memory. Microcontrollers, mostly almost all microcontrollers that you have heard about has its own memory. If you look at the washing machine, if you look at the microwave, if you look at your even the smartwatch, has its own memory, has its own program inside that particular memory. Okay, आप जब reset करते हो, then again after that it will resume to the previous loaded programs, है ना? वो change हो जाता है. Can I shift the processor which is available in microwave into the washing machine? No, because that has a fixed program inside it. Okay, so that processor will work according to the given program, given control. Okay, so that is dedicated for a particular task. Microcontrollers are dedicated for a particular task. Okay, in that particular case it must have the internal memory. Can I shift the processor of my PC to your PC? That means it is not dependent on the memory. Okay, it doesn't have its own program. Whatever control, whatever command I will provide it to, it will work accordingly. Okay, So it is general purpose processor. So this is microprocessor. Okay. So here you can see that this particular system is simply representing the microprocessor system, and microprocessor system based architecture is represented by von Neumann architecture. So this particular architecture which is shown to you is nothing but the von Neumann architecture. Okay. And if CPU has its internal memory, then that is called as Harvard architecture. Okay. So microcontrollers are based on Harvard architecture, and this general purpose computers are based on von Neumann architecture. Okay. Now look at this. So CPU has certain control unit, data path. Okay. And we must have certain input and output. So input devices are connected and output devices are connected. Lots of devices are there as classified input and output, and some devices are there that act as both. Okay. Like simple LED works both. Okay. Speaker works both. स्पीकर का डायाफ्राम हम यूज कर सकते हैं बोलने के लिए भी, ठीक है, और उससे जो ऑडियो प्रोड्यूस होता है दैट इज यूज्ड फॉर हियरिंग. ओके, सो बोथ multipurpose can be done. Touch screen uses as display devices as our output system. We also use to touch to give the command. Okay, that both works as an input as an output. So that depends upon the device property. Okay, that depends upon the device property how it is going to be classified. Okay, so I'm not jumping into that particular example. Just let me know whether it is synchronous or not. Whether it is synchronous or not. Asynchronous. How? But every time whenever you start processing anything, it produces the corresponding outcome to you immediately after the command. Okay, it doesn't like ki, I have given a command 3 day back and it is giving me the response now right now. Okay, so every processor is connected with a crystal clock. You if you can recall 8086, 8085, if you have studied about the microprocessor, there you can see that one clock is connected with a certain frequency to synchronize the entire process. See, if your computer device is asynchronous, in that particular case, whatever command you are going to say, let's say I have given a print command and someone has given some other command, it is having chaos which one is to be processed because it is not synced. Okay, so process management will also be done when your system is synced with respect to the time. Okay, so it is synced, it is very much synced. Okay, and to have the real time outcome, we have to study about the real time operating system. Okay, so we are not discussing about the real time, we are discussing about the whether it is synchronous or not. So your processor is very much connected with the crystal, a clock which is going to synchronize the entire process. Without clock it is in asynchronous. Okay, without clock you cannot predict the outcome. It is going to be appear right now or it is going to come after certain duration. Okay, so you cannot expect the processing of that. All right, so everything is dependent on the signal to synchronize or to produce the outcome or to supply some input. Everything is dependent on signal. Okay, so certain input signal is there, certain output signal is there, certain controlling signal is there. So clock signals, okay, that is nothing but represented in discrete like this one. So this is the clock signal 1 0 1 0 and so on. Okay, so signal plays very important role how you are going to represent. So every physical quantity is represented by a signal. Okay, whatever I am speaking is the audio signal. Okay, whatever you are observing from this particular screen is video signal. Okay, and how it is processed by a CPU, that is again input and output signal. Okay, so my speech can be the analog. My speech can be the analog. Okay, it may have the representation like this. It is discretized by the CPU. Okay, it is discretized. So on every time stamp, it is going to have a sample on this particular line. Okay, and you can discretize it. Okay, so this is the discrete signal. Whatever analog signal has been converted into discrete signal. So one circuit is required to convert this particular analog to digital, and that is called analog to digital converter. And whenever you want to observe this particular outcome, that is further converted from digital to analog, so that is required digital to analog converter. Okay, so your CPU is able to understand both analog as well as digital, and to represent it to the human readable format, in that particular case again you need to have certain converters. Okay, so the translators are playing very important role in converting one particular signal to another, and the processed one into the readable or understandable format. Okay, so for digital system, like I just told you that my CPU is going to be able to understand the digital term only. Okay, in that particular case your digital system requires the values in discrete format. Okay, so this is the continuous information. This helical shape is nothing but the continuous information, and in that particular case I am just converted into the discrete with respect to a particular timestamp. I just converted into the discrete values. Okay, now there are only two levels corresponding to the discrete values, only two levels that I have just represented over here, that it is going to be either 1 or 0. Your information is either present or not. Okay, whether switch is on or off. Okay, there is no intermediate state between that. There is no fuzzy. Okay, there is no fuzzy thing. So fuzzy logic जहाँ हम पढ़ते हैं, that is entirely different thing, that is related with the emotion, that is related with the certain membership, that is related with the certain chaos, possibilities. Okay, and apart from that particular possibilities, there is only two things: whether it is true or false, whether it will happen or not. Okay, so it is 0 or 1 only. All right, and that 0 1 is simply represented as binary. Okay, because this is two value only, in that particular it is known as binary values. Okay, is that clear? So binary values can be represented in digits as 0 and 1, or it can be represented in words as true and false. It can be represented as symbols as low or high, or it can be represented in words as on and off. Okay, the meaning of all these terms are same. Okay, so 0 is off, false. Okay, and this is low. ट्रू के केस में it is going to be 1, true, high, on. All right, so whenever there is terms related to this in throughout the course, you will treat it as simple, true or false, 0 or 1, and so on. Okay, so binary values are represented by the values or range of the values in a physical quantity. So any value of any system can be represented in binary term. Okay, whether it is audio signal, it is video signal, it is let's say any value in any particular term, any physical quantity, weight. Okay, any unit can be simply represented in binary term by simply converting it into the binary system. Okay, so like if you relate with the CPU, we can have the binary value physical quantity as voltage. Okay, now voltage can vary. It is of 0 volt, it is of 5 volt, it is of plus 5 volt, or it is of negative volt, and so on. Okay, so voltage fluctuation can be simply represented by the binary values. Disk में कैसा होता है? How the values are represented in disk? Electromagnetic field होती है ना? So that is represented as magnetic field direction. So that magnetic field can be further marked as 0 or 1. Okay. If there is an impression, that is simply counted as 1, otherwise it is 0. Okay. And CD, compact disc, again the same thing. Surface has a layer of something, okay, and whenever rays falls over that, it will simply read whether there is 0 or 1. There is bits or lights. Okay. In dynamic RAM, it is simply electric charge. If your condenser is charged, that will be counted as on. If it is discharged, it is counted as off. Transistors. Okay. So accordingly, like RAM is classified as static or dynamic. So depending whether it is using the capacitor or it is using the transistors. Okay. So based on that particular device uses, accordingly it is classified as static or dynamic. Okay. And depending upon that particular state, it is represented as on or off, whether it is charged or discharged. Okay. So that is all about your binary system or your physical quantity, that how physical quantities are related and how we can simply convert it into the binary term. Okay. Now representation, how number systems are represented in any particular base. Okay. Let's say we have decimal base. Okay. So what I am saying that I have a value, let's say 2, 3, 4, 5, base 10. Okay. And here we see that this is the unit value. Okay. Then this is the decimal value, hundredth place, thousandth place, and so on. Okay. And if I write it into the expanded form, it is nothing but 2000 plus 300 plus 40 plus 5. How it comes? It is nothing but 2 into 10 to the power the corresponding position, and position is marked from the least significant digit. So it is marked as 0, 1, 2 and 3. Okay. Fourth position is represented by value 3. Okay. So 2 into 10 to the power 3 plus 3 into 10 to the power 2 plus 4 into 10 to the power 1 plus 5 into 10 to the power 0. Okay. So any number is represented by its positional value. Okay. Its positional value with respect to the base. So in decimal number system, base is 10 और इसका रेंज कितना होगा? 0 to 9, 0 to 1 lesser than the base. तो कोई भी नंबर सिस्टम हो, ठीक है, whether it is 10, it is R, it is K, any number system. Okay. So this is for the integral part. Let's say if we have the value like 0.123, in that particular case, how it is represented in decimal system? 1 into 10 to the power minus 1. So here it starts from minus 1, minus 2, minus 3 and so on. Okay. So 1 into 10 to the power minus 1 plus 2 into 10 to the power minus 2, or what we can say, we can simply write it into the expanded form as 1 upon 10 plus 2 upon 100 plus 3 upon 1000 and so on. Okay. So it is simply converted it like 1 into 10 to the power minus 1 plus 2 into 10 to the power minus 2 and so on. Okay. So we can generalize it according to this, that whatever is the numeric value. So here you can see that the number is simply represented by digits from A. So A0, A1, A2, An minus 1, An minus 3 and so on. Okay. So this is the positional representation of the digits. Okay. After before this dot value. Okay. Before this fractional part, and this is representing -1, -2, minus m minus 1, and so on. So this is the fractional part represented over here according to the position. Okay, so whatever digit is there, ai multiplied by r to the power I, where I varies from 0 to n minus 1 for the integral part. Okay, for the integral part, if I start with like this, if I expand this particular equation, I can see it is a0 r to the power 0 plus, so I'm writing it in reverse direction to have a representation like that. Okay, a1 r to the power 1 plus a2 r to the power 2, and so on. Okay, now add the fractional part, a minus 1. Now it starts from minus m to minus 1. Okay, minus 1 to minus m to minus 1, or minus 1 to minus m. Is it so? Whether this representation is correct or not? फर्क नहीं पड़ता, इंक्रीमेंट या डिक्रीमेंट का फर्क पड़ेगा बेटा. -1 is the highest value in negative. Okay, so it says sum from least value to the higher one. So it is again sum from the least value to the higher one. Okay, रिप्रेजेंटेशन हमारा डिफरेंट हो सकता है, बट जब समेशन फॉर्म में या शॉर्ट फॉर्म में लिखते हैं, देन दैट मस्ट बी द करेंट. ओके, सो इट इज a टू द पावर -1, बेसिकली स्टार्ट होना चाहिए था a टू द पावर -m to r टू द पावर -m. ओके, प्लस a टू द पावर -m -1 -1 -1 or +1? +1, because every time whenever we add, it is going to reach to 0. Okay, so it is minus of m plus 1 to the power r to the power minus m plus 1, and so on to a to the power -1 to r to the power -1. Okay, so this is the generic representation of any number in base r, any number in base r. Okay, similarly for we can go for binary also. Let's say we have a binary number 1110.1010. So I can simply represent it as 1 into 2 to the power, let's say 0 1 2 3 3, plus 1 into 2 to the power 2, plus 1 into 2 to the power 1, plus 0 into 2 to the power 0, plus 1 into 2 to the power -1, plus 0 into 2 to the power -2, plus 1 into 2 to the power -3, plus 0 into 2 to the power -4. So any number system in any particular base can be, okay, all right. So any number system in any particular base can be represented by this generic formula. Is that clear? Shall I proceed? So look at this. So this is the general representation, and this one is very much familiar to us, that is represented in decimal. Okay, that we use daily life. And this is the binary number system which is accepted by the computer. Okay, so just look at this. Radix is simply represented as 0. So this is the power corresponding to the values. Okay, so it is 0 to r minus 1, it is ranging from 0 to r minus 1. So r to the power 0, r to the power 1, and so on. And in decimal number system, our digits can range from 0 to 9, and in binary system it can range from 0 to 1 only. For base 3, 0 to 2. For base 6, 0 to 5. Okay. So 1 lesser than the given base. All right. So that must be known to us, that for any random base, we can have the value from 0 to 1 lesser than the base value. Okay. That must be the range. If we have that particular relation, if we have the uh, given previous formula, we can easily convert any particular base to any one. We can calculate the unknown values from that particular given question. Okay. So like simple number system conversion or number system representation in gate exam is straightforward, not asked. Okay. It is given into some other ways, some other components are missing from that particular number. Okay. Any particular digit is missing. Okay. That digit is supposed to be calculated, that base is supposed to be calculated. Okay. So this concept is required, very much clear to you. Now this table you can memorize. Okay. This table you can memorize, like 10 to the power 5 is, that means simply it is representing 10 followed by so 1 followed by 5 0 digits. Okay. And if it is 2 to the power 5, it is simply represented 32 and so on. Okay. So this will help you to directly calculate the numeric value. Okay. Faster calculation you can do by this. Okay. Like if I represent it like 2 to the power 0, 2 to the power 1, 2 to the power 2, and so on. Let's say 2 to the power, let me complete it. Okay. So if I convert it into the decimal one, we can simply see it is going to be 1, it is 2, this is 4, 8, 16, 32, 64, 128, 256, and so on. Okay. Now what we have to do? We have to simply identify the positional one. Okay. Let's say I have the value like 10111. So we need not to multiply every time by 2 to the power something to know. Here we can do simple arithmetic addition. It is 16 plus 4 plus 2 plus 1. So you have to sum the corresponding positional one value. Ignore zeros. Okay. So if you have such kind of computation power, if you have such recalling, you can do the calculations very fast. Okay. So every time we need not to compute it like 1 multiplied 2 to the power 5, 2 multiplied 2 to the power 5, and so on. Okay. So special powers of zeros like 2 to the power 10. Okay. So we know that it is 1k. So 2 to the power 20 is, if 2 to the power 10 is 1k, then 2 to the power 20 is simply 2k. Okay. What we can do, 2 to the power 20 is nothing but 2 into 2 to the power 10. Is it so? Then k square. That means 2 to the power 10 to the power 2. So that computation must be done. Okay. Like if numbers are multiplied, powers are going to be added or powers are going to be subtracted when it is divided and so on. Okay. That arithmetic on powers must be known to you. So 2 to the power 20 is mega. Okay. 2 to the power 30 is giga. Okay. So it looks like a power is simply multiplied by 2, power is simply multiplied by 3, but it is having a very great impact, that it is power of power. Okay. It is not simply the numeric value multiplied with the fixed base. Okay. So it is having the power of power, and that is drastically changing. So your uh, kilo is simply converted into mega if it is simply squared. Okay. If it is simply cubed, it is converted into giga, and so on. Okay. So that kind of thing is required to be known to you. So just have the memorization of this particular base. Okay. So if exponent is this much, your value is going to this much. Okay, तो ये थोड़ा सा आपको याद होना चाहिए. Clear है? So by this way we can do faster computation. All right. So number based conversion, like we have some familiar things, like we have binary, we have decimal, we have octal and hexadecimal. What if we have a number in base k to be converted into base r? K and r are entirely different from these four. So we must have the right conversion, that from k to known one. Okay, it is not necessary to be decimal only. Decimal is very much familiar to us, that's why we are able to convert it into decimal, and then from decimal to r. Okay, that is very much easy way. Okay, now to know this particular conversion, okay, to come to this concluding remark, we must have the conversion between these defined terms. Okay, so from binary to decimal, binary to octal, binary to hexadecimal, and so on. Okay, we must have the conversion from these two terms. Okay, all right. So binary to decimal, how do we convert binary to decimal? For each and every digit in binary must be multiplied by power terms of 2. Okay, for any particular binary system, it must be multiplied by power terms of 2 according to its position. Okay, whether it is decimal or it is fractional or integral part. Okay, so let me have this example here, that convert 11010 base 2 into base 10. So just do it faster and let me have your answer. 26. How did you do this? Just simply adding the positional value. Okay, that is only possible if you have recalling of that particular power terms. Okay, so this is 0, 1, 2, or we can have the value corresponding to this, like it is 1, 2, 4, 8 and 16, and 16 is included, 8 is included, now 2 is included, so we have to add this. So it is 16 plus 8 plus 2, that is going to be 26 base 10. Okay, otherwise traditionally what we do, 0 into 2 to the power 0 plus 1 into 2 to the power 1 plus 0 into 2 to the power 2 plus 1 into 2 to the power 3 plus 1 into 2 to the power 4, and this is nothing but 16 multiplied 1, so that is 16, plus 8 multiplied 1, so it is 8, plus 4 multiplied 0 is going to be 0, plus 2 multiplied 1 is 2, plus 1 multiplied 0 is going to be 0. So ultimately it is giving me the same value. Okay, but in that particular case we need to have to perform this much computation. Okay, and if you can recall the positional value, you can directly have the sum of all the corresponding values. Okay, so this will be faster. All right, so everyone got the same answer? Yeah, thank you. So that was binary to decimal. Okay, let me go back, let me have one fractional value here. Let's say 10.1110 in base 2 convert into base 10. So that is going to be simply, if I convert this particular part, it is going to be 2 base 10, and for this particular term we have to apply this 1 into 2 to the power minus 1 plus 1 into 2 to the power minus 2 plus 1 into 2 to the power minus 3 plus 0 into 2 to the power minus 4. So this is going to be 1 by 2 plus 1 by 4 plus 1 by 8 plus 0. Okay, so that we can say it is 0.5 plus 0.25 plus 0.125. Okay, and that is going to be 0.875 base 10. So entire result is going to be 2.875 base 10. Okay, so rather than having computation of this particular value, it has a very fixed value. Okay, every time it is going to be fixed. 1 by 2, 1 by 4, 1 by 3, 1 by something. Okay, and ultimately that conversion is going to be multiplied by 1 or 0. So you have the fixed value corresponding to that particular position. Okay, so there is no harm to memorize this. Okay, rather than every time computing that particular value using the calculator, wasting the time, you can have the remembrance of this particular value. You can memorize this and you can directly put this value and get the answer. Okay, so this is decimal to binary, conversion from decimal to binary. What it says, I'm using the some different method. Like this particular method says that subtract the largest power of 2. Okay, subtract the largest power of 2 that gives the positive remainder and record that particular power. Okay, so that is the first step. Repeat subtracting from the prior remainder, recording the power. Until your remainder is 0. Okay, place ones in the position of the binary result corresponding to the powers recorded. So this is sometimes very looking like complex one, you know, but it is very easy. Just let me have the value over here. So we have 625 base 10. I just want to subtract it 2 to the power largest k. Okay, 2 to the power largest k, which is closer to 625. So which value is closer to this one? Come again? 624? 2 to the power? 2 to the power 9. Okay, so it is going to be 625 minus 624. 624? No. 512. Okay, and the power is 9. Okay, so this is nothing but 2 to the power 9. Okay, whatever is the remainder over here? 113. Okay, now repeat the step. 113 minus 2 to the power what? Can't be 128. So it is 64. That is 2 to the power 6. So power term is 6. Okay, remainder is 49. Now again repeat the process. 49 minus 2 to the power something, 32. That is 2 to the power 5. Remainder is 17. Position is 5 here. So 17 minus 16, that is 2 to the power 4. Remainder is 1 over here, and position, that is, remainder is this 1 minus 2 to the power 0, 1 minus 1. Okay, that is 2 to the power 0. So the remainder is 0 and power term is 1. So just write down the positional value of this. So I have just shown you that it is 2 to the power 0, 2 to the power 1, 2 to the power 2, 3, 4, 5, 6, 7, 8 and 9. Okay, just write the 2 to the power term. Okay, and whatever power term you have observed over here, just place 1 corresponding to all these observed power. So this is going to be 1, 6 is going to be 1, 5 is 1, 4 is 1 and 2 to the power 0 is 1. All other terms are 0. This is nothing but the conversion in base 2. Okay, so this is the easy method, but that is going to have the recalling of that particular power term. Okay, you have to have the remembrance of 2 to the power term so that you have the decimal value which is closer to the given numeric value. Okay, so this is one traditional method. If you can memorize the 2 to the power term, okay, in that particular case you can apply this particular concept. All right, so it is simply identifying the 2 to the power term, and corresponding power term you can simply place 1. Okay, and rest of the terms is simply represented as 0, so you can simply convert it into this one. Okay, so this is one traditional method. Now let me have the another method that we are very much familiar to, that one. Okay, 625. So I'll just uh, go to that particular thing. All right, so 625 base 10 is simply converted into base 2, and that traditional method says that divide this by 2 and just maintain the remainders over here. So 2 3 is 6, 2 1 is 2, 2 2 is 4, and remainder is 1 over here. Then 2 1 is 2 5 is 2 6 is, remainder is 0. 2 7 is 2 8 is, remainder is 0. 2 3 is 2 9 is 18, remainder is 0. 1 is and 9 is, remainder is 1 over here. Come again. 2 9 is, remainder is 1. 2 4 is, remainder is 1. 2 2 is, remainder is 0. 2 1 is. All right. So divide this, and now you have to place the values accordingly from bottom to top. Okay, just place the value. It is going to be 10111 00001. Okay, so this is going to be the least significant bit, and the first computed remainder is nothing but the most significant bit. Okay, so this is 0 1 2 3 4. What was the previous value?
I think it's inverted. So I think it is inverted. Like there should be 2 zeros. Because after dividing.
Okay. I further has to divide this. Okay, so it is 100. That is why positional mismatch was there. Okay, so here inverted like
from So it should be 10011, not 1000.
Let me check. Let me check. All right, all right, all right. Correct. So this is nothing but the LSB, and this is going to be the MSB. Okay. Extremely sorry for this. So it is going to be 100 followed by 111 0001. All right. So this is 0, 1, 2, 3, 4, 5, 6. Yes. 7, 8, 9, 9. So the corresponding position is matched with the previous one. Okay. Is that clear?
Yes.
Okay, let me have the fractional one. 10 point. Okay, we are converting decimal to binary. All right. 1, 2, 3, 4 base 10 into 2. So like this integral part, we have just seen the two mechanism that we follow anyone. Okay. So either by subtracting the highest power term of the two and identifying that particular power position to place 1, or we can divide it by the required base, okay, and just store all the remainders. All right. But for the fractional term, every time we have to multiply it with the 2 and record the integral part. Okay. So we need to have the multiplication like 0.1234 multiplied with 2, and it is going to be 8642.0. So integral part is 0 over here. Okay. Again multiply it with 2, that is going to be 4.0. All right. Repeat this particular process. Now, how long you can repeat this? How long? How many times? Either till fractional part becomes 0, or if it is not going to be converted into 0 in that particular case, we must have the floating point precision. Okay. So like 2 place, 3 place after the decimal, or so that must be defined. Okay. So if it is defined like uh, give the fractional part up to 2 decimal places, 3 decimal places, okay, by truncating or rounding of the values. All right. Or if it is repeated in nature, let's say every time in your conversion it is going to be appeared as 0.1010, 1010 and so on. Okay, so here you can have the pattern. Okay, 1010 is every time repeated, so we can truncate it after first appearance. All right. Or if it is terminated on 0. So three possibilities are there, whether there is a repeated occurrence of any particular pattern. So after the first pattern, we can simply truncate it by placing 3 dots after that. So that will indicate that this particular pattern is going to be repeated infinite time. Okay. Or it is terminated over 0. So there is no need to care about anything. Or if it is defined by the decimal place. Okay. 2 place, 3 place floating decimal position, in that particular case you can truncate your computation. Okay. So I'll go for 2 more. Okay. Because I can have the 1 as an integral part in that particular case. So 2 3 is 6 plus 1 7. Sorry. All right, again multiplied with 2, then it is going to be 4 15, 2 8 is 16 plus 1 17, 2 9 is 18 and 19. So it is going to be this much. So I can place the value over here as so this is 10, how it could be represented? 10. So it is going to be 1010 dot 0001. Okay. I don't know the corresponding next value, so I'll just truncating it over decimal 4 places, and it is going to be the equivalent conversion into the binary one. All right. Okay, so this is the radix given to the corresponding known number systems. So binary radix is 2, digits are 0, 1, octal base is 8, and values ranges from 0 to 7. For decimal it is 0 to 9. For hexadecimal it is 0 to 9 followed by alphanumeric term. Okay, so A is representing 10, B is representing 11, and so on. So in decimal number system it is simply representing 10, 11, 12, and 15. Okay, but in hexadecimal system it is simply represented in alphabets. Okay. All right. So that I advocated already, that you must have the memorization of some basic terms in any particular number system. So here you can simply consider like 10 is represented like this in base 10. Your numbers up to 16s are represented like this. Why it is 16 only taken? Because that is going to be converted into base 16. Okay. If I just want to convert 16 in base 10 into hexadecimal term, in that particular case it is simply represented as 10. Okay, you can have the computation of that one. Okay, so just look at this. So my device is causing some issue, let me resolve it first. All right, so this is 16 base 10 requires in value in hexadecimal. Okay, so what I can do, I can simply convert it into binary. Okay, or the procedure that is followed in the previous example, that divide it by the required base and just record the remainders. Okay, so 16 is divided by 16 and record the remainders. 16 1 ja, and this is 0. Okay, so it is 10 base 16. All right, this is 1 followed by 0, so 10 in base 16, which is the required value over here. Okay, and in octal number system, 16 2s are and 0, so it is nothing but 20 in base 8. All right, what if I convert it into binary? Let's say 16 base 10 is simply converted into binary, so that is going to be 1 followed by 4 zeros. Okay, now if you want to convert it into octal, just start comparing, combining this three terms, because octal is represented in binary as 2 to the power 3. Okay, so 3 digits at a time, starting from the leftmost significant bit. Okay, significant bit. So just combine 3 bits at a time. So this value is going to be converted into 0, and this value is simply representing 2. So that is converted into base 8. Start combining the 4 terms. Okay, so if it is not having the previous value, you can simply assume at 0 before this. Okay, so this is going to be 1 and it is 0 into base 16. Okay, let's say it is base 32. Then it is nothing but simply 5. Okay, So accordingly you have to compute. 5 होगा? नहीं भाई. 5 digits. You have to combine 5 digits. Okay. So this value is going to be 16 itself. है ना? Okay, so conversion between the bases says that we can convert from one particular base to another one. Okay, and that follows the following steps: convert the integer part, convert the fractional part, and join the results. Okay, that we have already seen. For the binary number system, we have done this. So just look at the example here. So yeah, come to this part. So convert the integral part simply by dividing into the required base. So whatever new base is required, divide the given number by that particular base, store the remainders, arrange them according to the order. Okay, and multiply the fractional part by the new radix. Okay, and every time store the integral part. All right, for integral part you have to recall the, you have to restore the remainder terms. For fractional part you have to multiply and store the integral parts of that particular multiplication result. Okay, repeat this particular process. Now let me have this particular value 46.6875 base 10. Convert it into base 2. So 46 divided by 2, 23, remainder 0, then divided by 2, 11, remainder is 1, divided by 2, 5, remainder is 1, 2 to the 4, remainder is 1, 2 ones are, remainder is 0. Okay, so this is going to be 101110 base 2, that is the integral part. सेम आ रहा है आप सबका? Now apply for this particular fractional part. 0.6875 multiplied by 2. So 2 is the required base. 0, 5, 7, 13. So 1.3750. So 1 is this particular part. So after decimal, 1 will be there. And then for this particular fractional part, again repeat the process. 0, 0, 5.7. So 0 is the integral part over here. So that 0 is recorded. Then 0.75 multiplied by 2 is going to 1.50. So again 1 is recorded over here, multiplied by 2, it is going to be 1.00. So the fractional part is terminated by 0. Okay, and now we need to just record the integral part of this. So after computation of these two tasks, you have to combine the results. So the combined result is going to be 10111 followed by 0 dot 1011 for base 2. Okay, I guess my pen is not working properly, so it is causing some issue. Is that clear? Okay, so these are the concerns that we have already discussed corresponding to the fractional part. Okay, that fractional part is either terminated with 0, not going to be terminated, or there is some repetition happening every time. Okay, just look at this particular example, like 0.65 base 10 converted into 2. So here you can see that once we start converting it to the binary term, we need to multiply 0.65 by 2. Okay, and just record the integral part, and after the particular time you can see that 1011 is nothing but the recurrence of that. Okay, sorry, here it is 011, sorry, 001. 001, 001, 001 is repeated occurrence every time. Okay, so rather than computing this repeated occurrence up to infinite time, we can truncate it up to a certain time. Okay, let's say twice it is repeated. Okay, twice it is repeated, and you can simply truncate it by putting 3 dots. Okay, indicating that it is further going to be repeated. Okay, so you have to have the certain mechanism to truncate your value rather than going to be computing, because in gate exam you do not have the much time. Okay, so you have to reach to the conclusion very fast. So if there is any such kind of appearance, you just try to identify the pattern. If it is repeated occurrence there, you can terminate over there. Okay, all right, just cross check. How can you cross check whether your outcome is correct? Convert the converted value into the decimal one, okay, or the original base, whatever was given, okay, by simply multiplying and dividing. Okay, so converting into according to the given formula, that the previous formula that we have seen. Okay, so the positional r to the power, positional power of that. Okay, the value multiplied by the positional radix. All right, till now, if you have any doubt, any question, anyone has any question till now? Yes, no? All right. So by the same way, by the same mechanism, we can follow for the conversion from octal or hexadecimal to binary, or from binary to octal or hexadecimal. Okay, the same procedure. We can convert binary into decimal, and then from decimal to octal or hexadecimal. Okay, that is one traditional way. Or we have the relation between the binary, octal and hexadecimal that I have just shown you, that any binary number system can be represented in a 3-digit pair of octal, okay, or 4-digit combination in hexadecimal. Okay, so we can apply that particular mechanism to convert binary into octal, hexadecimal, or octal to hexadecimal, or into this one. Okay, so we can apply the shorthand method rather than dividing or converting into decimal and then converting into the required one. Okay, so we'll follow the shorthand mechanism to convert this. Okay, let's say this is the value given into the octal. I just want to convert into the binary and into the hexadecimal. All right, so whenever we just want to convert into binary, again we have to represent each and every number in the octal term into 3 binary digits. All right, so 5 can be directly represented as 101, 3 can be represented as 011, 6 can be represented as 110. All right, 1 can be represented as, doesn't matter whether it is before the fractional part or after the fractional part, you have to follow the same process. It is 001, 7 is represented as 111, this 7 is again represented as 111. Okay, so it is simply converted into binary. Place the dot at the corresponding position. All right, now it says you have to convert it into hexadecimal. So hexadecimal के लिए मैंने क्या बोला था? Apply 4 combinations. Okay, 4-digit combination. So 4-bit combinations are there from LSB. Okay, so you have to follow that. So there are 3 combinations before this dot value. So integral parts has 3 combinations. Now for fractional part, again start from the least significant bit, or you can say the fractional position, dot position. Okay, so start from this, 1 combination, 2 combination, and third one. So the value is going to be 1, 9, and this is 8 plus 1, 9 plus 4, 13. 13 is represented as D. So 19D as an integral part. Now let me check the fractional part. It is going to be 3F8. Okay, so if I combine this, the result is going to be 190 dot 3F8 into hexadecimal representation. All right. If anyone has any doubt in this conversion, see, you have to be very careful. If I'm saying start converting from the least significant digit, that means you cannot start with the fractional part. Okay, if I start combining from the fractional position 4 digits from this particular place, your answer will be wrong. Okay, because we can afford zeros preceding into the integral part, we can afford zeros appending in the fractional part. Okay, but we cannot afford in reverse direction. That will change the numeric value. Okay, so appending zeros in integral part at the MSB side, appending zeros at the fractional part in LSB side is feasible. Okay, so for fractional numbers you have to start from the dot position. Okay, dot to left for the integral part, dot to right from the fractional part. Okay, why this conversion works? It is because the binary number system positional representation has the direct relation with the octal and hexadecimal. Okay, 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 16, and this is 8. So this power term is representing the combination. 3-digit combination is simply representing the octal. 4-digit representation is simply representing the hexadecimal. Due to this particular relation, it is easy to convert from binary to octal or to hexadecimal easily. Okay. So you can use the arithmetic in other bases. Okay, like you can see, just convert this into base 10. Convert this particular number into base 10. So this is the binary term 10111 base 2, and that you want to convert into base 10. So we have seen the traditional method, 1 multiplied 2 to the power r minus 1 and so on, that we have already seen, plus 0 into 2 to the power something and so on. This is very much traditional way. We can apply the arithmetic on binary system itself. Base 10 can be represented in the binary as 1010 base 2. This is equivalent to 10 in base 10, isn't it? If we have the numbers in same base, we can directly apply the multiplication or division. Okay, but that will be little complex. So rather than jumping into that particular complex thing, we'll follow the traditional one. Okay. So here you can have the division like 10 111 is divided by 1010. Okay. and that has the quotient as well as the remainder. Okay. Again, quotient is further divided by this. We have remainder and the, sorry, this is the quotient and the remainder. Okay. Now, since you have the remainders, you have to simply arrange them. Okay. So this is the MSB and this one is the LSB. You have to simply arrange them. Okay. Once you have arranged, convert it into the required decimal term. So this is 4 and this one is 6. So it is converted into 46 base 10. Okay. So in this particular case, what it requires, whenever you divide every time, you need to have the corresponding quotient and you have to subtract. So you have to have the knowledge of borrow and so. Okay, dividing binary numbers in 2 digits, dividing, subtracting. Okay, and in that particular case, you have to care about the borrows. Okay, so rather than jumping into that particular complex thing, it is better to follow the traditional one. Okay, we can do this. We can do this into the known number system. When it is unknown number system, it is going to be little complex. Okay. So we have seen the mechanism of converging one particular base to another particular base. Okay. Till now it is familiar one. We know each and every base. We know binary, we know octal, we know hexadecimal and so on. Okay. What if it is unknown base? Change to known one and then convert it into the another required one. All right. So let me have this first question from the GATE exam. GATE 2024, CSE 2024, say 2 question. Which of the following is R equal to 2 to 4 in radix 5? Okay, so radix or the base is 5 over here. The numeric value is 2 to 4. You just have to convert this value into the given options. So what we can do? Convert this 2 to 4 base 5 into decimal one first. So let me convert this. This is 2 to 4 base 5 into base 10. So it is nothing but 2 into 5 to the power 2 plus 2 into 5 to the power 1 plus 4 into 5 to the power 0. That is 50 plus 10 plus 4. That is going to be 64 base 10. Your first option is correct. Okay, but the question says whether it is or. You have to be very careful about the question. That means it is nothing but MSQ. Okay, if more than one option is correct, in that case it is going to be MSQ. So since it is known to us, we can directly convert it into octal. Now this base is known to us, we can convert it into octal. What we can do, we can simply convert it into octal by converting into binary. 64 is this one is base 2. Okay, combine the 3 terms. Okay, so it is going to be 100 base 8. Okay, 100 base 8 is 100 in radix 8. Option B is also correct. Since we have the binary value, we can check for the hexadecimal also. So 4-digit combination, it is going to be 4 0 in base 16, which is not the given option here. So C is not the correct one. D is also correct. So what you have to do, you have to divide this 64 by base 7. 9 ja, and this is going to be 1. Okay, remainder is 1. Divide it again. 1 ja, remainder is 2. So 1 to 1 in base 7. That means third option D is also correct. So we have 3 correct options in this particular case. Is that clear? So you have to read question very carefully and see whether only one option is correct or it is demanding whether there are more than one possibility. Okay. So if so, you have to check for all the possibility. You have to check all the options. Okay. Now in this particular case, you can see that 3 options are correct. And this is just came into the previous exam. Just 1 month before. Solve it. This is GATE exam 2023. This particular question appears in GATE 2023. A particular number is written as 132 in base 4. The same number in radix 5 is represented as what? So 132 in base 4 is required to be converted into base 10, and then we can convert it into base 5. So first convert it into base 10. It is 1 into 4 to the power 2 plus 3 into 4 to the power 1 plus 2 into 4 to the power 0. That is 16 plus 12 plus 2. That is going to be 30. Okay, so this is 30 base 10. Okay, and 30 base 10 is 16 plus 8 is 24 plus 4 plus 2. That is, okay, we need not to convert it into binary. So this is the binary one. Okay, we just need not to convert it into binary. Okay. So what we can do, we have 30 as base 10, divide it by 5 to get the corresponding value. 5 6 are 30, 0, 5 1 ja, and it is going to be 110. Okay, so 110 is the required answer in base 5. Okay, so if such kind of questions are there from out of 4 to 5% or 4 to 6%, you can directly get this question. Okay, any doubt till now? Anyone has any doubt? Okay, let me have some complex one. This is the question in GATE 2015. Consider the equation 43 base x is equals to y3 base 8. Okay, so the question is 43 base x is equal to y3 base 8, where x and y are the unknown values. Okay, so the number of possible solutions is, how many solutions are possible for this particular question? Okay, what are the possible values or the combinations of x and y's are there? You have to simply have the count of that. Okay, it is not asking for the value of x and y. It is asking for the possibilities of x and y so that this particular relation is valid. Okay. So first you have to find the relation between these two. Just check about the values, positions of the x and y. X is the base over here. Okay. And the values are 4, 3. That means x cannot be lesser than 4. Okay. Cannot be lesser than or equal to 4. So x should be greater than 4. Okay. That is one observation from this particular equation. And the value of y should be less than or equal to 7 or less than 8. Is that clear? Okay, that is one thing. Now we need to find the relation between x and y. Then only we can have the conclusion about the values. Okay, so we have to solve this equation. 4 into x to the power 1 plus 3 into x to the power 0 is equals to y into 8 to the power 1 plus 3 into 8 to the power 0. Just solve it. So it is 4x plus 3 is equal to 8y plus 3. 3 cancelled out. Okay. So it is 4x is equal to 8y, or we can say x is equal to 2y. All right. And we have these two observations as well. Include the next one, x is equals to 2y. Now start picking the values corresponding to x and y so that we can have the possibilities. How many number of solutions are possible for this? Can we take x as a 1? We cannot, because it cannot be less than 4. Okay, even 4 cannot be taken. Okay, so can we start with 5? Okay, let me have the value of x as 5. If it is 5, then y is 2.5. Can it happen? Can y be the fractional value? Y cannot be the fractional value. Y is always integer over here. Okay, so x is 5 is not the solution here. Okay, so think about the possible values. Now look at this, x cannot be greater than 7. So can we think of such value which can actually x is equal to 6? Okay, let me have x is equal to 6. Then y is 3. Okay, which is lesser than 7? That is also valid. And x is greater than 4, which is also valid. So this is one possible solution. Go for the next value. Can it be 7? No. Let it be 8. Then y is 4. Okay, that is valid. Go for the third solution. X is 10. See, odd values cannot be accepted because that is going to have the fractional value of y. Okay, so we cannot go for the odd value of x. Okay, so these things you have to observe from the solved equation. Okay, so y is 5 over here, which is again valid because it is lesser than 7. Okay, go for the next one. X is 12, y is 6, again valid. Go for the next one. X is 14, y is 7, which is equal to 7. which is affordable. Can we go for 16? Y is going to be 8 and the value cannot be equal to its base. Okay, range cannot be equal to its base. So it is not the required solution. This one is also not required its solution. So there are 5 possible solutions for this particular question. So possibilities are 5 here. The number of possible solutions are 5 in this particular case. Okay. If it is clear, we'll proceed. We'll further proceed if anyone has any doubt. All right. Go for the next question. This one is the question in set 2 of 2014. Very much similar to that question. Okay. But in that particular case, x and y are at the different side of the equation. Now it is on the same side. X belongs to the range of y. So consider this equation 1, 2, 3 base 5 is equal to x 8 base y, where x and y are unknown. Now again you have to find the possible solutions. How many possible solutions are there? Okay, I just want to have the answer from you. Okay, just solve it, and after this we'll have 5-minute break and then we'll continue further. Four solutions. We have one answer that we may have the 4 solutions. Okay, I'm just writing down over here. Let others to have the answer.
I'm getting 3.
Okay, someone is getting 3.
Yes, sir. 3.
3. Okay. Okay, meanwhile, I'm also solving this particular question. Let me check. So it is going to be 25 plus 10 plus 3 is going to be 38 base 10. All right, which is equals to xy plus 8. All right, so this is 38 is equal to xy plus 8, and it is xy is equals to 30. Now x cannot be greater than or equal to, so sorry, x should be less than y, and y could be anything. Y could be greater than 8. Okay, so we have the relation over here, and now I just want to have the answer. Okay, so let me have the possibility like x should be greater than 8. Okay, sorry, y should be greater than 8. So here we cannot take any value lesser than 8 for y. Okay, so I can have 9, but 9 multiplied something is not going to be equal to 30. Okay, so I can take value 10 over here. So 10 3 is going to be 30. So x is going to be 3 here and y is going to be 10. Okay. Now let me have 11, 12, 13, 14. So up to 14, there is no solution for this particular equation. Okay. So I can have the value 15 for y. Okay. 2 will give me the answer as 30 over here. So x is 2 and y is 15. Okay. Similarly, 16, 17, 18, 19. Okay. Uh, 20, again, that is going to give me the value x as 1.5, which is not possible because that cannot be the fractional value. Okay. So from 20 to 29, there is no solution corresponding to this. Okay. So we can go for 30 as y. So x can be 1. So in that particular case, it is 30. So x is 1 and y is 30. Okay. Can we go further? X can be 0. But 0 multiplied anything is going to be 0, which is not equal to 30. We cannot go below this. Okay. We cannot go below this because it cannot be negative. Okay. So range varies from 0 to radix minus 1. Okay. So we cannot proceed further from this particular equation. So there are 3 possible solutions corresponding to this equation only. All right. If someone has some different answer than this, please let me know. All right. So you have 5-minute break over here. We'll continue from this particular slide.
When facing an exam like GATE, the stakes are really high. Tough competition, limited opportunities, and lots of hope riding on your shoulders. Geeks for Geeks understands the pressure. And to ensure that you have the best support system to crack GATE CSE 2025, we have launched our latest batch taught by our GATE mentors with more than a decade of teaching experience and multiple GATE top rankers as their students. We know that you got it in you to crack GATE exam. Now all you got to do is commit to learning, commit with Geeks for Geeks. When facing
Hi, this new year we got a very special message for us. The message says, thanks GeeksforGeeks team for this amazing course. Just cracked government exam with AIR2 and got call for document verification. Excited for GATE 2024. This 2024 year has started well for me. These are the words of one of our students enrolled in GATE Computer Science course, and trust me, this not only motivate other students but us teachers as well to put in that extra effort. First of all, many congratulations Ishan. If you too are a GATE Computer Science 2025 aspirant, I invite you to check out our GATE CS course. Till then, keep learning. Hi. This new year, we got a very special message for us. The message says, thanks GeeksforGeeks team for this amazing course. Just cracked government exam with AIR2 and got call for document verification. Excited for GATE 2024. This 2024 year has started well for me. These are the words of one of our students enrolled in GATE Computer Science course, and trust me, this not only motivate other students but us teachers as well to put in that extra effort. First of all, many congratulations Ishan. If you too are a GATE Computer Science 2025 aspirant, I invite you to check out our GATE CS course. Till then, keep learning. Hi, this new year we got a very special message for us. The message says, thanks GeeksforGeeks team for this amazing course. Just cracked government exam with AIR2 and got call for document verification. Excited for GATE 2024. This 2024 year has started well for me. These are the words of one of our students enrolled in GATE Computer Science course, and trust me, this not only motivate other students but us teachers as well to put in that extra effort. First of all, many congratulations Ishan. If you too are a GATE Computer Science 2025 aspirant, I invite you to check out our GATE CS course. Till then, keep learning. Hi, this new year we got a very special message for us. The message says, thanks GeeksforGeeks team for this amazing course. Just cracked government exam with AIR2 and got call for document verification. Excited for GATE 2024. This 2024 year has started well for me. These are the words of one of our students enrolled in GATE Computer Science course, and trust me, this not only motivate other students but us teachers as well to put in that extra effort. First of all, many congratulations Ishan. If you too are a GATE Computer Science 2025 aspirant, I invite you to check out our GATE CS course. Till then, keep learning.
शुरू हो गया है
So online students, please let me know if they are came back to their seat. We can start further. Just raise a thumbs up. All right. So this is the question that we have just solved, and check whether there is any possibility. So such kind of questions are every time there in the GATE exam. Okay. So 1 marks or 2 marks question is there always, similar kind of questions that to either compute the value of x or y or find the possible solutions. Okay. So you may have one possible answer out of that, whether that is indicating x and y value or the total number of possibility that you have to compute. Okay. Okay, this is another question that is from set 1 of 2014. So the question is, the base of the number system says that the following equation holds. Okay, you have to determine the base so that 312 divided by 20 is equal to 13.1. Okay, so you have to compute the base. Since both side base is not known to us, so you can simply say both the sides, left hand side and right hand side, must be same. Okay, so it is nothing but 312 divided by 20 base, let's say x is equals to 13.1 base x. So you have to compute the base x for this particular question. It looks very easy, but that has a minor trick, and if you ignore that particular trick, your answer is going to be wrong. So I'm just expecting your answer first, and then I'll solve it. So do we have any answer? Please write in your chat box so that I can see. See, we cannot simply divide it or multiply it. So just if I just want to have simplifying this particular equation, we cannot divide 312 by 20 because we don't know the base. We don't know how much remainder is permitted. Okay, so we cannot go for the division on this. Okay, even we cannot multiply it with 13.1. 20 cannot be directly multiplied with 13.1 again because we don't know after multiplication how much value is going to be shifted as you can say the value which is carry, okay, which is overflowing. Okay, so the carry term we don't know base. Okay, in that particular case we cannot easily solve it by simply dividing or multiplying it. Okay, so what we can do, we can simplify it into the known base. We can solve it for the base 10. Okay, so I can simply convert it like this much: 3 multiplied by x square plus 1x plus 2, and this is divided by 2x plus 0. All right, this we can do. Now for this particular section again we can do this: 1 into x plus 3 plus 1 upon x. This we can do. Now base is known to us. Base of both sides is known to us. Now it is base 10. Okay, we can solve it. Just do it. It is going to be x square plus 3x plus 1 upon x. All right, now we can cancel out this particular x with this one. Okay, expand this particular question. So it is going to be 3x square plus x plus 2 is equal to, because 2 is over here left, so we can multiply it with the next term. It is going to be 2x square plus 6x plus 2. Okay, now just simplify the term. So it is 3x square minus 2x square plus x minus 6x plus 2 minus 2 is equals to 0. So it is cancelled out. The term left over here is x square minus 5x is equals to 0. Or we can write it like x into x minus 5 is equals to 0. So there are two possibilities that x is going to be 0 or x is going to be 5. Okay, x cannot be the 0 because we have certain values that lies within this particular range, 0 to x minus 1. So x itself cannot be 0. Okay, so this is not the possible answer corresponding to x. Now x could be 5. Out of these two possibilities, x could be 5. So the base for this particular number system should be 5. Wasn't it very simple question? Representation only makes it complex. Okay, it looks like complex, but it is very simple question. So whenever you are stuck in any particular situation that the base is not known to us, we are not able to determine what should be the borrow corresponding to the division or what should be the carry corresponding to the multiplication. Why I am saying this? Borrow corresponding to the division or carry corresponding to the multiplication. ऐसा होता है क्या? मल्टीप्लाई करते हैं तो कैरी आता है, डिवाइड करते हैं तो बोरो आता है. Multiplication is nothing but the repetitive addition, है ना? And division is repeated subtraction. That is why whenever you divide anything, you need to have the division every time, subtraction every time, and you have to record the borrow. Okay, and whenever you are multiplying every time, you have to add and record the carry. Okay, so if base is not known to us, we cannot determine this borrow or carry. So it is better to convert the number system into known base. Okay, any known base, and better is to convert it into decimal. Once it is converted, we are very much familiar with the base, borrow and carry. Okay, and we can perform the operation. Now we can compute the value of unknown term. All right. Find the equivalent of this. GATE 2009. 1217 base 8 is equivalent to which one? Now, in this particular case, it is not known to me that whether it is MCQ or it is MSQ. You have to go for both. Because there are two different bases. If every answer is like all the options are in base 16, in that particular case, there will be only one correct option. Okay, but since base is varying, you have to go for both. Okay. So conversion in base 8 to base 16 is very easy. Just convert it into binary and then rearrange the number of bits. 1217 in base 8 is going to be simply 001, 010 and 001 and then 111. Start combining 4 terms from LSB and you can see that it is 28F base 16. So option B is the correct one. Now, since option B is correct, then A and D cannot be the correct one. Okay, because they have the same base. Base 16 may have only one correct option. Okay, now go for base 10.
Not correct.
So what is the value in base 10? 655. That's it. 655 base 10, which is not matching with the given option. Okay, so there is only one correct option for this question. 1217 base 8 is 28F in base 16. All right, that is the only correct option. All right, so till now we have seen the number system. Okay, and why the number system is required? Because our discrete system is going to accept the known format, the discrete number system. Okay, and that is the binary term. And because in our daily life we are not only dealing with the binary system, we may have any particular base, so we need to know the conversion from one particular base system to another base system. Okay, so we have covered till now the discrete system, the binary number system, decimal number system, octal and hexadecimal number system, or any particular unknown base. Okay, and the conversion from one particular base to another base. Okay, so if anyone has any doubt till now, please let me know, because that number system and conversion is over. Number system and its conversion from one particular base to another base is over. Please let me know if anyone has any doubt. So you have seen the variants of the questions that may appear in GATE exam. Okay. Determine the unknown base, determine the unknown range value. Okay. Or both, or to find the possible solution of the given equation. Please indicate if you do not have any question. Clear? All right. So binary coding, like if we are talking about the binary number system, we can represent any large value into 0 1 combination. Okay. And determining or observing certain outcome from that particular number system is not going to be easy. Say you have million of 0 1 0 1 combination, can you easily convert that particular value into your known format? You can predict any particular value. It is not going to be so easy. Okay. So what it says, we can have certain constraint with combination of these binary values, so that uh, if we apply that particular constraint, we can easily determine the coded information. Okay. That's why it is called as binary coding. Okay. So that restrictions is applied on a particular combination of binary digits, so that we can determine the particular code. Let's say in terms of octal and hexadecimal, we have seen just now 3-digit combination or 4-digit combination. If we apply certain set of rule, certain set of constraint on binary number system, we can easily decode that particular binary number. Okay. So your unique interpretation of that particular value can be done if your number system or binary system is coded. Okay. That's why it is called binary coding. Okay. So let me have certain example of that. Just look at this. The non-numeric binary codes are represented like colors are represented in the binary values. Okay. Red is represented as 000. So 3-digit combination is taken to represent any non-binary number. Okay. So the range red, orange, yellow color information can be represented. We can have certain similar other information like uh, let's say 10 numbers are there. Okay. And these 10 numbers are having certain relation between these uh, each one of them. Okay. We can represent them as a ascending to descending order or descending to ascending order by certain number of bits. Okay. Or let's say we have certain processes, they have certain priority in each of them. Okay. So what we can do, we can represent these priorities by the binary bits. Okay. Let's say 4 priority values are there. Okay. So what we can do, we can take 2-bit representation 0001 10 and 11 to represent the 4 possibilities. Okay. By this we can represent their priority. Okay. 00 is the least priority, 11 is the highest priority. Okay. So any information can be simply represented in binary term by applying certain restriction. All right. So how many number of bits are going to be represented in that? For m possible solutions, we can have 2 to the power something which is relating this m. Okay. For 8 colors, we need to have only 3 bits. For 4 priorities, we need to have only 2 bits required. Okay. For 16%, only 4 bits are required. Okay. So similarly, we can represent any unknown term into the known one by restricting the combination of number of bits. All right. Now just jump into the known one, decimal number system. We know the range from 0 to 9. If I restrict it to be represented by the 4-bit binary, then it is simply known as binary coded decimal. That is simply known as binary coded decimal. So 4 bit can be represented up to 0 to 9. But from this particular 4 bit, we can further represent 10 to 15. 10102 all ones. Okay. So they will be treated as, because it is restricted, it is conditional. Okay. So we say that from 10 to 15 are not desired solution. Okay. Or we can say it is don't care. Okay. So such kind of restriction we have to impose on the binary number system so that we can convert it into some coded information. All right. So this is just representation that given n digit in radix r. Okay. So we have just to determine the number of digits na. So for given n digits in radix r, there are r to the power n distinct element that can be represented. Okay. तो ये थोड़ा सा आपको समझने में दिक्कत हो रही है तो मैं आपको बताऊं. Let's say we have a microprocessor which has address line 20. Okay, 20 address lines. कौन सा माइक्रोप्रोसेसर? You can answer. 8086. Good. 8085 has only 16 address lines. Okay, and 8086 has 20 address lines. Okay, from this 20 address lines, how many addresses can be represented? If I represent this 20 address lines like starting from 00, कितने हो गए? 16, 20. So this is 20 address lines, all representing 0, and it can go up to all 1. है ना? The values can range from 0 to all f. है ना? How many numbers are there? For 2 digit, 00, 01, 10, 11. It is 2 to the power 2. 4 possibility. For 3 digit, 000 to 111. 2 to the power 3. For 20 lines, 2 to the power 20. Okay. So for n digits, for radix r, it is r to the power n distinct elements are there. Is that clear now? Okay. So for this particular r to the power 1 n, we can have the further possibilities. So we have seen this particular information, and here for this you can see that for 4 elements in radix 2, we can have the values 0001, 0010, 00 this and this. Okay. तो ये सारी हमारी जो values है, they are represented at radix 2 but in 4 digit. Okay, base 2 in 4 digits. So base 2 in 2 digit is represented like this, base 2 in 4 digit is represented like this, base 2 in 6 digit can also be represented. Okay, so how many values, the useful information can be represented in base 2? Only 4. Okay, only 4. 0, 1, 2, 3. That's it. Okay, rest other information is don't care, because every time you are just appending number of zeros. All right. So the second case is also known as one hot code. Okay. So that is just a representational information. Why it is so? It is just representing in this particular case, it is representing the positional one, because there are only 4 informations, 2 to the power 2, radix 2 to the power 2, binary number system है ना, ठीक है? तो in that particular case it is going to represent only 4 information. तो अब यहाँ पे 4 information आपका represent हो रहा था 0001 10 11 से. Okay, that is the actual binary code. Okay, Now in this particular case, it is representing the actual positional code. Okay, so here 1, 2 at second place, 1 at third place, 1 at fourth place. Okay, so this one is representing the 1 hot, that means 1 is at the hot position, 1 is at the positional system. Okay, look at this. So we have the decimal value, decimal range starting from 0 to 9. Okay, 8421 code. This is one code which is known as 8421 code. It is also called as BCD, binary coded decimal. Okay, so 0 is represented as 4-digit 0, 1 is represented as 4-digit 0001, 9 is represented as 1001. Okay, so any decimal number system represented by 4-digit or nibble is called as BCD code, or it is 8421 code. Why it is 8421? 16842 क्यों नहीं कह दिया? Place value 2 to the power 0, 2 to the power 1, 2 to the power 2 and 2 to the power 3. 8421. That's it. Okay. Excess 3, by the name itself, whatever is the current value plus 3. Okay, whatever is the current value plus 3. So 0 plus 3, 2 plus 3 and so on. Okay, just look at the value. Just check the value. I'm just picking the random value. 5 plus 3, 9 plus 3. Okay, so this is excess 3 code. Whatever is the current value of the BCD plus 3 is giving the value. 84 minus 2 minus 1. Now you have to compute the value accordingly. Okay, for 0, everything is going to be 0. For 1, 0, 1, 1, 1. Why it is so? You have to add the possible terms, possible positional values, so that the outcome is 1. Okay, so just look at this. 4 plus minus 2 minus 1 is going to be 1. Okay, so these 3 digits are playing the role to compute the value 1. Okay, so you have to place value 1 at that particular position to get the corresponding value. Okay, for 2, 4 minus 2 only is representing the 2. So 0, 1, 1, 0. Okay, for 9, all 1. 8 plus 4 is 12 minus 3. Okay, gray code. So just let me have one example here. Let's say 4 is represented here as this one 0, 1, 0, 0. So gray code is computed as, so place this MSB as it is. Okay, and now add this two adjacent term. 0 plus 1 is 1, then 1 plus 0 is 1, then 0 plus 0 is 0. So for corresponding value 4, gray code is going to be 0, 1, 1, 0. So just check the value corresponding to this. The gray code is 0, 1, 1, 0. Why it is important? Okay, why these codes are important? We'll see this particular task in next lecture. What is the significance of these codes? How these are useful in our daily life? Okay, why it is important for the GATE exam? Okay, we'll continue from this particular topic tomorrow onwards. Okay, so far, if you have any doubt related to your GATE exam, related to this particular topic covered, please ask. So I'm closing this session today. Okay. The next class will be theory of computation. That is from 12:30. I guess that is from 12:30. So if you have any doubt till now, please let me know. All right. So content is given to you. Visit your login. Okay. All right. So that will again come into the course tomorrow. Let me have one example here. Okay. So let me have the value here. Let's say the values are 1, 2, 3. Let me write here. So these are the decimal values and these are the corresponding BCD. Okay. This is the corresponding BCD. Okay. My pen is not. Okay. So this is the corresponding BCD. Okay. So I'm just going to convert into gray code, and gray code is nothing but the conversion from BCD to gray. Okay. So in this particular case, let me have the value, let's say 000. For 000, if I convert into gray, so for 0000, you have to just place the MSB value as it is at the MSB position, and then MSB to the next one is simply added. Okay. And then added means or. Okay. You need not to care about the carry. Okay. Like if it is 1 1, then it is going to be what? 1 0. So you have to place only 0. Okay. You need not to bother about the carry. Okay. So now in this particular case, it is 0 0. So it is going to be 0. If it is again for the same case, it is 0. For the next case, it is 0. So just add them and the result is going to be placed. Okay. So for 0, gray code is going to be 0. Okay. Let me have the value 6. Okay. For 6, it is going to be 0 1 1 0. Okay. Place the MSB as it is. 0 1 is going to be 1. Okay. 0 added with 1 is going to be 1 here, and then all right, add with the next one. 1 1 is going to be 1 0. Okay. So some value is 0, that is going to be placed over here. Okay. And then 1 0 is going to be 1, so that is going to be placed over here. Okay. I guess some okay. Okay, this is so this is from BCD to gray. Okay, this is BCD to gray. Now if you want to convert from gray to gray, okay, for 5 the gray value is this much, 0 0 1 0. Okay. For 6, what you have to do, you have to simply substitute this 0, then add with this 0, add with this is going to be 1, and for this it is going to be 1. Okay. So if you are computing from gray to gray, in that particular case your answer is going to be matched. Okay. The concept of the gray is to have 1 bit difference in the previous and current value only. Okay. If you look at the scenario, uh, 5 is having 0010 and 6 is having 0011. Okay. So it says that there is only 1 bit difference in the previous and the current value. Just look at the any one. 6 and 7, only 1 bit toggle. Okay. 7 and 8, only 1 bit is misplaced. Okay. So this is the error detection code. Okay, this is the error detection code which is very much helpful in further coding. Okay, तो इसका एग्जांपल मैं आपको दूंगा. सी अगर आप कन्वर्जन देख रहे हो BCD to gray, that will be entirely different because we are dealing with the BCD value. Okay, when we are dealing with the gray code, in that particular case your answer will be definitely different. Okay, so these are the relation between the two term. This is conversion accordingly to BCD to x3 to 8 to 4, 8 4 minus 2 minus 1, and then equivalent into gray. That's why your values are entirely different. Okay, that's why you are not able to correlate with this particular gray value. So I'll come to this particular topic again in the next lecture. We'll show you how to convert this gray value from scratch. Okay, just don't correlate with the particular table with the value. Okay, this is just for example how decimal is converted into BCD and BCD is converted into x3, then that x3 is converted into or into different form also. Okay, so I'll come to the same topic again, how this number systems are, how this coded information is represented corresponding to the values. Okay, and what are their significant in your digital logic course. Okay, any further question? Okay, so I'm closing this session today. See you in the next class. Till then, bye.
When facing an exam like GATE, the stakes are really high. Tough competition, limited opportunities, and lots of hope riding on your shoulders. Geeks4Geeks understands the pressure. And to ensure that you have the best support system to crack GATE CSE 2025, we have launched our latest batch taught by our GATE mentors with more than a decade of teaching experience and multiple GATE top rankers as their students. We know that you got it in you to crack GATE exam. Now all you got to do is commit to learning, commit with Geeks4Geeks.
Hi, this new year we got a very special message for us. The message says, thanks Geeks4Geeks team for this amazing course. Just cracked government exam with AIR2 and got call for document verification. Excited for GATE 2024. This 2024 year has started well for me. These are the words of one of our students enrolled in GATE computer science course, and trust me, this not only motivate other students but us teachers as well to put in that extra effort. First of all, many congratulations Ishan. If you too are a GATE Computer Science 2025 aspirant, I invite you to check out our GATE CS course. Till then, keep learning. Hi, this new year we got a very special message for us. The message says, thanks Geeks4Geeks team for this amazing course. Just cracked government exam with AIR2